the experimental result being bigger than the theoretical result, the reporter replied that it was due to errors in measurement which were small enough to be negligible. And for the friction, eddy current, and the slipping, rolling motion of the approaching ball, the reporter replied that all of these are negligible enough, since the only external force acting on the system is the friction force. So, pointsmiths. Although they shared a great intellectual debate, they missed to point out what the definition of keywords such as the magnet's position and the other sources of energy loss and how they could have affected the results. So it could have been better if the reporter added some various parameters and added numerical calculation for energy loss, and for the opponent, he should have focused more on the experimental approach and the effect of other parameters.
Okay, thank you for the review. The reporter team, you have 2 minutes to make your final concluding remarks.
First, I want to thank both the opponent and reviewer for good suggestion, and now I'll wrap up my research. First, during the discussion, there was some discussion points, and about the rotation energy, I answered to the opponents that it is conserved during the attraction phase, and it is not transferred to the last pole, which I will discuss in the next slide. And also about the magnetic force measurement, it is not the main focus of the problem. It is just for evaluating the magnetic potential energy of the ball and magnet, and that was what I used. And about the magnet position, I changed the number of poles in front of the magnet and behind the magnet. So I think these two variables represent the magnetic position as very well. And also about the rotational energy, the only way for the last pole to gain angular velocity is the friction between the pole and the other pole. And if you calculate the impulse of this, it is very small. Sorry, I didn't put the equation, but the impulse is very small. It is about 10 radian per second, and it results in velocity change less than 0.01 meter per second. And also, about the magnetic force measurement, I think there was some misunderstanding, so I fixed the string and cooled it. So, in summary, my theoretical model, it considers the energy loss and energy dispersion, which is very realistic. And also, it can precisely predict the ejection speed within error 5%. Finally, about the optimization of the magnetic position, I found out that in my system, it is optimized with 3 or 4 bolts behind the magnet. Yeah, and it could be also applied to other cases. Thank you for listening.
Thank you all three teams for a wonderful discussion. Now the members of jury will take 10 minutes to ask you some simple questions.
Okay, I have a question to the opponent. You mentioned that magnets shouldn't be fixed, or shouldn't need to be fixed.
Yes.
Why should it be fixed in your case?
In the case, as the reporter has mentioned, if the magnet is not fixed, then the momentum of the magnet should be considered the ejecting velocity. However, if the magnet is fixed, then if you can ignore the movement of the whole rail, then you can consider that the ejecting velocity will be much faster than the case where the magnet is not fixed.
If the magnet is fixed, then what would it cause?
So, if the magnet is perfectly fixed so that it does not have any movement, there's no way for the magnet to transfer the energy, but in real cases, there can be small deviations, and also that could result in higher ejection velocity, because as I predicted in my conservation laws, the energy from the magnetic potential also goes to the the kinetic energy of the balls moving backward, and that will be diminished. So,
What's the mass of magnet?
mass of magnet is 26 grams. So the steel ball is 28 grams, but I considered in my theory. 28.
I think this problem focuses on the equation of magnet, but I want to ask you the mass of magnet. What's the optimized mass of magnet?
So in this case, the reason why I use the magnet with same mass is that the problem says a sequence of identical steel balls includes magnets, and I guess that the magnet should also look identical with the steel ball. And I think even though the mass of the magnet increases, my theory still applies, and I could predict the ejection velocity as well.
You show me the experimental setup for measuring the magnetic field.
And field.
Force.
Force.
Well, where the distance was d, and the distance was between the two magnets or from the center.
So it's the center of mass.
From center of mass to the center of mass.
Yeah. So
Then in that case, one is magnet and the other one is magnetized forward.
Yeah.
Then you can expect how it varies because magnetic field, magnetic force is inverse proportional to the distance, and then the magnetic dipole moment is inversely proportional to the distance q, and then total will be the magnetic energy will be inversely proportional to the distance tips, and then you can differentiate that one and you will obtain the magnetic force inversely proportional to the distance 6. But you obtain to the 8th power, right? What does discrepancy between
as I said, the magnetic between the magnetic dipole and dipole, maybe the force will be inversely proportional to the 6th power, the distance to the 6th power. But in this case, I think the most major problem is that the magnetization of the steel ball varies with the distance. So I guess that if the distance is too far, the magnetization is small, and if it gets closer, it is big. So that will cause additional currents.
I mean the magnetization where magnetic dipole moment is proportional to the distance q. That's already varying according to distance, right? Distance q, inversely proportional to distance q, 1 over r3.
I'm not sure.
And then where you can get the textbook. And then also the magnetic field will be inverse square root of forces, right? So that means 1 over r squared. And then the energy will be, potential energy will be the magnetic field times the magnetic dipole moment, right? That will be 1 over r2.
I admit that I lack theory about the magnetic theory, but in this case, there is actually a paper about this force measurement, and the paper also gives to the distance to the power minus 8. So I admit that I don't know the exact relationship between the force, but I think it is not major problem in this problem because it is considering just about the magnetic potential energy, and even though even if we do not fit, we can just approximate using like trapezoidal method or others.
I have a question for you. Did you measure the magnetic potential energy each time? How many times did you measure the magnetic energy?
So
One is enough?
So there is error bar, and I measured it 5 times for every trial.
Each step you must have you may have a different magnetic energy. Did you check the magnet which setup?
The magnet I use is all the same, so I don't think it's much.
I have a question for all three of you. Opponent, I think the previous two questions is pertinent to what both you and the reviewer pointed out. At the initial condition, which way is the magnetization direction for their setup, and did they make sure it's always that way?
Could you clarify your question again, please?
What is the direction of the dipole of the magnet and the magnetized balls at the initial condition?
In the initial condition, the dipole of the magnet is in the dipole of magnet. The ball approaching the magnet is in the direction of the magnet, and therefore, as the ball approaches the magnet, I think, it will be the same.
The reviewer?
When the first ball is released at a certain distance away from the magnet, it becomes magnetized in the same direction. However, as it starts to roll, it is constantly being affected by the magnetic field, so the magnetic direction changes.
But the simpler question is, they have a spherical magnet. Which way is it? Which way is north pointing on that magnet? And did the reporter constantly use the same orientation? No, that's the question to the opponent and the reviewer. Or does that matter?
I think that matters, as the reviewer has mentioned. As the ball rotates, the direction of the North Pole matters, because the potential energy is given as the dot product of magnetic moment and the magnetic field. Therefore, the angle between those magnetic moment and the field will matter. The initial condition, the magnet will matter.
Okay, so what do you think was the initial position of the magnet?
I think the initial position of the magnet would have been arbitrary in each experiment.
Is that true?
No, it isn't. So, actually, in fact, the magnetic force between the magnet and steel ball is about 30 Newton, which is very strong. So I put X mark on each poles of the magnet to check whether the steel ball always attached to the pole, and I saw that it always attached to the pole.
Okay.
Yeah.
And you changed your answer on whether the magnetic force is conservative or not. Do you understand why the opponent and the reviewer asked you that question?
So, I think that the opponent, so in my opinion, the magnetic force is conserved, but in fact, and in real detail, since the steel ball is ferromagnetic and it shows some kind of hysteresis, so it is not perfectly conservative, but I assume that those effects are small, so that I can approximate the magnetic potential energy gain as it approaches the magnet.
Is that the reason that you asked them the question?
Yes.
Really? Not about the integration of to get the potential?
One of the things is that, the fact that he used magnetic potential means that he assumed that he thought that magnetic force is conservative. That I wanted to ask why he assumed that.
Reviewer, same?
Could you please repeat the question, please?
Why did you point out about whether the reporters flip-flopping on the question of whether the magnetic force is conservative or not? Why is that important to the discussion?
Why the direction of the magnetic force is
No, why the magnetic force is conservative or not?
Because it counts for it could count for the energy loss in the system, and it greatly affects the velocity of the launching ball.
Are there any other short questions? No? Okay, then we'll tally up the scores. Everybody's ready? Scores for the reporting team. 8, 8, 10, 8, 9, 9, 8, 8, 8, 9. Scores for the opponent team. 7, 8, 8, 7, 8, 8, 8, 7, 6, 9. And scores for the reviewer team. 7, 7, 8. I can't. 7, 8, 8, 8, 7, 6, 7. Okay, I'd like to thank all three teams for a wonderful discussion.